All right, I'd like to again thank you for this conference. It's been really fun and really interesting. It's great to have an opportunity to expand the way we think about things, because so often we spend our days thinking about very narrow topics that we're specialists in. So this has been an opportunity. Also, geographically, I'd like to move us from China and India, where there are terrible pollution problems, to think about Northern Europe and maybe California as sort of a paradigm to think about what we'll be talking about. So what I'm going to discuss is the grid-connected home energy hub, which could fundamentally transform the way that we get access to energy in the future. So I'd like to quickly acknowledge the people who did a lot of the work on this. Marcus Felgenhauer he's actually at Technical University of Munich, but spent the time at Stanford, another postdoc, and Thomas Hamaker, who is the designer of the model that we used in these studies, also BMW for support. Okay, so let's talk about today's electricity system. The home is essentially a passive consumer of electricity. Not only that, we're a passive consumer of natural gas for heating typically, and we go to a gas station to fill up our car. So basically the home it provides energy services, but it in a very passive way. So if we look to the future, and actually the near future, and this is certainly happening over many parts of Europe and the United States, is that homes have now become energy producers, primarily through the addition of PV to your home. You can self-consume that, or you may sell it back to the grid, and other people will use it. So that's kind of where the emerging trends today. But if we look to the future, we can actually imagine quite a different scenario where our home really becomes an energy hub that provides for all of our needs. So our electricity for transportation, our electricity for everything else in the house, and that our thermostat is smart and so forth. And not only are we basically producing and consuming, this home energy hub is actually participating in a much broader market with regard to providing energy services back to the grid and getting compensation. So that last vision is what I'm going to be talking about today. So what are the drivers of change? Why are we going to do this? Well, decarbonization is a big one. Personal choice turns out actually to be a very big one, because often, at least in the short term, these things don't look very cost effective. Battery electric vehicles coming along and the need for basically home charging, that's where people do that. Real or perceived cost savings. The need for the electricity system to have more responsive loads, that we need to be able to control those and offer services back to the grid in our ability to do that. And then finally, there are some national, state, local mandates. In California, for example, they've now decided that all new homes will be zero net energy. You can question the wisdom of that, but nevertheless, that's where we are. Okay, so as we imagine this home system of the future, our home energy hub, we actually have a wide range of technological choices to make. For our electricity, we can have grid power, PV, we can provide electricity for batteries, we could even have fuel cells. With regard to heating, we can have natural gas, we can have direct electric heating, we could have heat pumps, we could have combined heat and power if we put fuel cells in our homes. And then with regard to vehicles, obviously internal combustion vehicles, battery electric vehicles, and fuel cell electric vehicles. So the question is, as we imagine this energy system of the future, this home energy hub, what are going to be the choices, the economically optimal choices that people are going to make, recognizing that portfolio of technology options are highly interconnected. So for example, if one were to have a fuel cell vehicle and you are producing hydrogen in your home to fuel that vehicle, you would have also options to sell hydrogen actually back to the natural gas grid. You can accommodate a certain amount of that. You might decide to have a fuel cell in your home for combined heat and power. And all of these are highly interconnected, and the economics of what choices we make need to recognize those. Otherwise, we will have suboptimal solutions. So that's the question we set about to answer. And we decided to look at this in the context of two different case studies, one for California, Northern California, but with very different climates, very different economic status, and so forth. And then we also picked two communities in Germany and Bavaria, but again, very different demographic, very different climate. And so basically what the model does is you have the inputs, so those are the renewable energy resources that are available. We also have to input lots of information about technology characteristics, and then we also have to understand demand. So for this particular model, we looked at the average consumer in a population. However, if one were to really do this in a more sophisticated way, that we would have similar demand data for different populations who behave differently. And then finally, the output is how much energy we're going to use, when we're going to use it, and what are going to be the technological options that we choose to do that. Okay, to make it somewhat simpler, we decided to limit one set of variables, and that is choices for transportation. So, and we looked at two different time frames. We looked in 2025 and we looked at 2035. And in the first set of cases, we looked at, for 2025, a penetration of 13% battery electric vehicles, 13% fuel cell electric vehicles, or a mix. And similarly, we have a much more aggressive scenario in 2035 where we look at 38% total penetration of these technologies. So that's what we looked at. So here's an example. These are optimized solutions for what people would actually do. On the left-hand side is the battery electric vehicle case. On the right hand is the fuel cell electric vehicle case. This looks just at the summer, but we do this 365 days of the year. And what you can see in both cases, we're using a lot of solar in the cost optimal solution. It's anywhere between 50 to 60% of total energy demand. We've introduced storage into the system. That's the green show there. You can see when we're storing and when we're using that stored electricity. And we're also charging our electric vehicles. For the fuel cell case, quite similar, but we're producing a lot of hydrogen for our fuel cell vehicle. So this is sort of what the solution looks like, and again, large PV deployment in both scenarios. So let's talk about some of the key results then. So this is a slightly confusing chart, but the top is the cost, and the bottom is the CO2 emissions. Okay, so we'd like to optimize both. This isn't a formal optimization of both, though. So the first thing to notice, if you look at 2025 and 2035, the cost to the consumers, even though that these large changes have been made, are relatively slim. They compare very well to the baseline case, which is the bar on the left-hand side. The second thing is if you look at the reduction in emissions and you compare that to the first to the first of the 2025 and first of the 2035 cases, that you can see that because the U.S. has such aggressive targets for improvement of transportation efficiency, the incremental value in terms of emission reductions of the vehicle switching is not terribly great. Okay. You also can see that there's not much of a difference between the emissions reductions achievable with an electric vehicle and a fuel cell vehicle. And one of the things, the detail buried in there is basically fuel cells are a lot more expensive. And interestingly, we found that all these potential co-benefits of producing hydrogen that could be used locally, they're too costly in the California context. So, and then heating. For the German cases, we see a large switch to electric heating, which again didn't happen in the California scenarios because we've got very, very cheap natural gas. Okay, so just a other interesting sort of facts about this. So if we look at the, so this is the cost per ton of CO2 reduction, comparing these scenarios. So we see by 2025, the battery electric vehicle case, almost no incremental cost, which is very, very interesting. And actually, a lot of the auto manufacturers are seeing this as a possibility. Fuel cell switching, particularly in the short term, over $600 a ton, very, very uneconomical. And if we look out to 2025, battery electric vehicles look like the lowest cost option, but again, fuel cell vehicle costs remain very high. So the bottom line of why fuel cell vehicles are, the costs of the system are so much higher is that you have to generate hydrogen, you have to store the hydrogen, and then you have to use the hydrogen in a fuel cell. Each of those has less than perfect efficiency, and when you multiply them all together, they're only about 30% as efficient as using your electric vehicle. The consequence is that you have to put in a lot more PV, like 2.5 times more PV to meet that energy demand. So that's the kind of future we may have. We may not, but we may. And if you think about this home energy system, now instead of having passive consumers, we're each going to need a home energy management system that will help us to optimize the use of the resources that we've got in our home. And it will need to consider lots of factors, our individual use patterns, weather, future weather, maybe even what our neighbors are doing and so forth. So there's a big data and society and systems problem. Second, there's another tier beyond this as we imagine this home energy hub participating in the electric market. There's the electricity market, there are all kinds of issues of how much data, when, how do you use aggregators, for example? So again, many very exciting problems. And really, this is a huge opportunity for data optimization. And I think for those of you who are students in the audience, this is a really exciting time to really imagine how the electricity system will change and how information and sensing and controls will help us do this in a much more environmental and cost-effective way. Thank you.
So one quick follow-up question, Sally. Have you looked beyond the individual household at neighborhoods? Say, suppose I start to aggregate over a couple of houses or a small community. Is there a cost efficiency in that, or?
Yeah, you know, I think there would be. We haven't done that yet. We're about to look at the entire state of California, and we may, look at sub-region. Yeah, it's a big. So we're going to the opposite extreme, but I do think it's a very interesting question.
Yeah. Okay.